Here we've got a solid put in contact with the gas. We know it's monoatomic, and the gas starts at a higher temperature, but it's going to presumably cool off, and the solid warms up till they reach a final temperature of 200 kelvins. And it looks like we're looking for what was the initial temperature of the gas. So we might not even have to care about the solid so much just yet. Our goal here is ultimately to find what was the initial temperature of the gas. So let's start by just writing out what we know there. We know that the final temperature of the gas is 200 Kelvin. We want to know what was T initial. And there's also a solid, but I don't know if we're actually going to need to know anything about the solid because it doesn't really tell us much about it anyway. But what do we know about the gas?
It's monatomic.
It's monoatomic. So let me make a note of that. What does that tell us about the gas?
3 modes.
Yeah, 3 modes per atom. And that's it. It's got the 3 translational modes and nothing else. We also know, what else do we know about the initial and final situations here?
The final thermal equilibrium.
Yeah. Well, we know the final temperature at thermal equilibrium is 200 Kelvin. But what else do we know about the behavior? I mean, all this stuff so far, the temperature is a macroscopic quantity. You can actually measure it. But what do we know about the microscopic situation? What's going on with the individual atoms?
The translational speed of the gas atom is half of its initial translational speed.
Exactly. The gas atoms have slowed down, and we know they've slowed down to exactly half the original speed. So let me make a note of that also. We know that for one gas atom, or any one gas atom, I want to say one average gas atom, because of course individual atoms are going to be different. They're not all traveling at exactly the same speed, but an average gas atom at the end, V final, is moving half as fast as its initial speed. So what do you think that's going to tell you about the temperature? Why would this be related?
I'm guessing that the temperature, well, I mean, it decreased.
Yeah, the temperature has definitely decreased, which corresponds to the atoms moving more slowly. And if we want to figure out exactly how much the temperature decreased by, we can use this idea that the speed has dropped to half the original amount. But what equations could we use to relate the idea of the speed of the individual atom versus the temperature of the gas? Do you have any equations that tie together the speed of the atom versus the temperature? Or like if you knew the temperature, how would you find the speed? Like, let's say you were dealing with maybe, I mean, this is monoatomic, so let's say for simplicity, it's just helium. If you had a cloud of helium and you knew it was at, let's say, 500 kelvins of temperature, how would you figure out how fast one helium atom is moving? What kind of energy is associated with the translational motion? What energy is associated with the speed of travel? Yeah, kinetic energy. Or yeah, exactly, kinetic energy. So if we want to know something about speed, we should be looking at kinetic energy. And that's exactly what these 3 modes are. Any single particle is going to have 3 translational modes, assuming it's able to move in 3 dimensions. So if we take a look at the three translational modes, one atom has, let me show you a different color. One atom, that's worse. There we go. One atom has three kinetic energy translational modes. And how much energy would you expect each one of those modes to have? What's the energy in one mode? R is really more talking about entire moles worth of atoms. We're looking at just one atom here, and in fact, just one mode within one atom. So what's the usual formula for the energy of just one mode? Or what should it be proportional to? Like, what is it about the system that determines how much energy each mode has?
Thermal energy?
That's the type of energy overall, but what's the indicator for that?
Temperature?
Yeah, energy per mode is all about temperature. Specifically, something times temperature. Higher temperature just means the modes have more energy each. Lower temperature means less energy per mode. If two substances are at the same temperature, that just means that their modes have the same amount of energy on average. Not the total energy, but the energy per mode. So energy per mode should just be some multiplier times temperature. And what is that multiplier? That's actually just going to be 1/2 kV. The three comes from the fact that we've got three modes. So we will have 3/2 kBT for the total kinetic energy of one atom. But the energy in one mode would just be 1/2 kV. So the energy per mode, and this coefficient is really just something you have to memorize. The general idea is that energy per mode should be dependent on temperature. That gives you energy per mode equals some constant times temperature. But that constant is just Boltzmann's constant over 2, half of Boltzmann's constant. But we do have three of those modes. Each mode has kB over 2 times temperature as the energy in that one mode. But we have three modes, so the kinetic energy per atom is going to be 3 times that, 3 times 1/2 kBT. So that is the kinetic energy of one atom, 3/2 kBT. And we can also set that equal to, what other formula could we use for kinetic energy here?
Could we use 1/2 mass times velocity squared, or?
Yeah, because that's the other usual formula for kinetic energy. The kinetic energy of one atom is just 3 times the energy per mode, because there's 3 kinetic energy modes in this atom. But we can also use the usual formula, half the mass times the speed squared. So we can say half the mass of the atom times the speed squared equals 3 modes times energy per mode. So this actually gives us a useful relationship between the speed of the atom and the temperature of the substance. But notice that speed is squared here. Speed is not proportional to temperature. Speed squared is proportional to temperature. And everything else is just a bunch of constants. So if we were to solve for speed here, or solve for temperature, because temperature is really what we care about. If you solve this for temperature, you're just going to get temperature equals a constant times speed squared. And we could actually find what that constant is by just multiply both sides by 2/3 kb. But we don't actually need to know that constant here. We just need to know how temperature and speed are related. And specifically, temperature is a constant times speed squared. And we can focus on just the temperature and the speed because these are the only things that are changing here. The temperature is going down and the atoms are moving more slowly. Everything else, the mass and the 3 and the Boltzmann's constant are all staying the same. Any questions on that formula so far? And what do we know has happened to the speed?
It's decreased.
Right. Specifically, it is decreased by how much?
Half.
Right. So if the speed has decreased to half of its original value, what would you expect to happen to the temperature as a result?
Half, maybe.
Not just half, though. If temperature were equal to a constant times speed, then I'd expect temperature to also drop to half the original amount. But temperature is not proportional to speed here. Temperature is proportional to speed squared.
Okay.
So if you multiply speed by 1/2, what's going to happen to that 1/2? If you just change speed to half the speed, what happens to that half when you square it?
I'm kind of confused about the question.
Which question?
Oh, just like the one you're asking.
What happens to the temperature?
Yeah.
We got to consider what happens to the temperature as the speed drops to 1/2. And that half, I think, is best thought of as a multiplier. We're taking the original speed and we're multiplying it by 1/2. So let's call this T initial equals constant times speed initial squared. T final would be the same constant times the final speed squared. But we know that the final speed is half of the initial speed. So if we replace V final with 1/2 times V initial, we're squaring 1/2 times V initial. The V initial gets squared, but the 1/2 also gets squared. And what do you get when you square 1/2?
1/4.
Right. So that means the final temperature will be 1/4 of the original temperature. Because temperature is proportional to speed squared, and the squared affects the multiplier as well. Because we are squaring the final speed, which means we're squaring 1/2 of the original speed. The squared affects both of those, the modifier and the initial speed. In fact, you could even write that out. You could say T final equals that constant times 1/4 times speed initial squared. But constant times V initial squared is just temperature initial. So we get 1/4 times temperature initial. In other words, final temperature is 1/4 times the initial temperature. So having the velocity leads to quartering the temperature because we're squaring that modifier. And this is generally true anytime one quantity is proportional to another quantity squared. Like for instance, if we multiply this speed by 3, 3 squared would be 9. So 3 times as much speed would mean 9 times as much temperature. Or let's say 5 times as much speed. You'd be squaring the 5, so you get 25 times as much temperature. The multiplier or divisor on temperature is the same as the multiplier or divisor on speed squared. And if we know that we took the initial temperature, decreased to 1/4 and ended up at 200, what was the initial temperature?
800.
Right, because we know the final temperature is the initial temperature over 4. And we know the final temperature is 200. Multiply by 4 and we get 800 kelvins. And we actually can multiply and divide temperatures if they're in kelvins. If the temperature's in Celsius, multiplying and dividing doesn't make sense. Like you can't say half of 30 degrees Celsius is 15 degrees Celsius, because Celsius is only about changes. The 0 on Celsius doesn't mean anything other than the freezing point of water. So if you're going to be using temperature as a multiplier or divider, it needs to be in kelvins or Rankine, but nobody uses Rankine as far as I can tell. So just keep it in Kelvin if you're going to be using it as with multiplication and division. Of course, if it's a change in temperature, then Celsius also works. But this isn't change in temperature. This is the actual raw temperature. Any other questions on that one?
Yeah, I have a question. I guess I'm a little bit confused about like the constant. Why does the constant not affect the final temperature?
It doesn't really influence the relationship between the initial and final situation because it's the same constant. If you actually solve for that constant, if we continue here, if you solve for temperature here, you get temperature equals, the 2's cancel out because we got to divide it by 2 on both sides. So we get mass over 3 kb times speed squared. So the temperature is just going to be, or the constant is just mass over 3 times Boltzmann's constant. But since it's the same mass over 3 times Boltzmann's constant in all these equations, we can just treat it as a constant that we don't really care about.
Okay, I see.
In fact, the reason why that cancels out in this case, if you take a look at the constant times 1/4 times speed initial squared, everything on this side of the equation except the 1/4, constant times v initial squared, is just the initial temperature. So we're essentially just doing a substitution here. If T final is the constant, in other words, m over 3 kb, times 1/4 times speed initial squared, that's the same as 1/4 times the initial temperature. So the 1/4 is really the important thing here, because that's the modifier between the initial temperature and the final temperature. Any other questions on that one?
So what exactly is the constant again?
That constant is just the mass over 3 times Boltzmann's constant here.
Oh, okay, I see.
But the important thing is in this whole equation, the m over 2 times speed squared equals 3 times Boltzmann's constant over 2 times temperature, the idea that the usual formula for kinetic energy equals the 3 kinetic energy modes for one atom times the energy per mode. In that equation, the only things that are changing from initial to final are speed and temperature. So everything else is just a constant multiplier. We don't really need to worry about which constant multiplier it is because we're not really looking at what the actual values are. We're just looking at how much they're changing. We don't care about what the speed is. We just know that it's changing to half the original amount. And because this problem is all about multipliers and dividers, just that the final is half the original amount, in other words, VI times 1/2, that means we can ignore any constant multipliers. They're still there, they're just not changing, so we don't really care about them.
Okay, that makes sense. Thank you.
Mm-hmm. And you could certainly write it in. You could write out these exact same equations, but actually include m over 3 kb as the constant. But you'll still end up with T final is 1/4 times everything from T initial. And therefore, final temperature is 1/4 the original temperature. Any other questions on that? And in general, I would highly recommend looking for proportionalities like this. Anytime you know that some quantity is proportional to another quantity or proportional to another quantity squared, try looking for how those are related. Then, for instance, if in this case we know temperature is proportional to speed squared. So whatever happens to speed as a multiplier, that same multiplier squared influences temperature. You multiply the speed by 10, the temperature gets multiplied by 100. You multiply the speed by 1/5, you get 1/25 of the temperature. because of these squared in the proportionality. Likewise, if this had been like temperature is proportional to something to the third, multiplying that something by 2 would result in the temperature being multiplied by 8 because 2 to the third is 8. So it's very useful to think of these, the relationship between quantities as proportionalities, and then look at how one of them is being changed as a multiplier or a divisor. Any other questions on that? All right, then let's take a look at problem number 2 from the quiz. Can you see this all right? Oh, wait, there. This one with the diatomic gas. So in this one, we've got 2 moles of a diatomic gas, and it looks like ultimately we just want the molar specific heat. And typically, how would you find the molar specific heat of a gas? Well, other way around, really. Molar specific heat means the specific heat per mole. CVM or CV mole, the heat capacity of 1 mole. So the difference there is heat capacity means the difficulty of changing temperature of the whole sample, regardless of how big it is, or I guess including how big it is, I should say. The heat capacity is the amount of heat it takes per degree temperature change of the whole sample, including its size. But the specific heat is the heat capacity standardized to 1 unit of the substance. So the mass specific heat is the heat capacity of exactly 1 kilogram of the substance. The molar specific heat is the heat capacity of exactly 1 mole of the substance. So that's really what we're looking for. We want the heat capacity of exactly 1 mole of the substance, which means we can probably ignore the fact that there are 2 moles. We don't care about the 2 moles. We want what's the heat capacity of 1 mole of the substance. And it says the vibrational modes are frozen out. How would the heat capacity of 1 mole relate to the number of modes? Do you have a formula describing how heat capacity per mole and number of modes are related to each other? Yeah, 1/2 times number of modes per particle times R. And I'm just going to write this as number of modes, but keep in mind that means number of modes per particle. And this formula automatically should standardize it to exactly one mole. If you want the heat capacity of the whole substance, that's going to be the molar specific heat times the number of moles. Because the number of moles times R over 2, that's the heat capacity of 1 mole. If you multiply by number of moles, you get the heat capacity of the whole thing. But this is specifically asking for the molar specific heat. So we're looking for the heat capacity per mole, not the heat capacity of the whole thing. Which means all we really need to do is find the number of modes. So how would we figure out the number of modes of these diatomic molecules in a gas phase trapped in this space between 2 plates? How many or what modes would we count here? What modes should we include?
Well, are there 3 kinetic energy ones?
What kind of kinetic energy?
3 kinetic translational.
Usually we would include 3 kinetic energy translational, but why is it usually 3? Like, why would we usually expect 3 translational modes per molecule?
That is a good question.
Yes, it is. I thought so too. Ultimately, it has to do with how the molecules are able to move. How many dimensions does our universe have?
Oh, it only has 2 dimensions.
This one is only 2-dimensional, yeah. Usually we expect modes, especially the translational modes, to come in sets of 3 because the object can be moving in the x direction, moving in the y direction, and moving in the z direction, or any combination of those, of course. Any diagonal is just going to be some combination of x direction, y direction, z direction. So in a 3-dimensional universe, such as the one we typically live in, unless you have some way of visiting others, we have 3 kinetic energy modes per particle. But these molecules are trapped in this effectively 2-dimensional space. They can move in the x direction and the y direction, but there's no z direction movement, no inwards or outwards from the screen. So we would expect only 2 kinetic energy translational modes. But that's not the only way this molecule can move. How else would this molecule be able to move? Like, for instance, this molecule, yeah, it can move in the sense of translational motion in the x direction and the y direction, but it can also move in a rotational sense. It can spin around its own axis. So how many rotational modes would you expect this molecule to have? We usually expect diatomic molecules to have 2 rotational modes because we live in a 3-dimensional universe. For instance, this stick can rotate around this axis, and it can rotate around this axis. So this sort of rotation. And rotating around its own axis of symmetry, of course, doesn't count because nothing's really changing. However, keep in mind these are constrained to only 2 dimensions. So let's say we're talking about this 2-dimensional surface. The molecule can rotate like this, but rotating like this would involve leaving that 2-dimensional plane. So this rotation doesn't count in this case because they're sandwiched between the planes. They can't rotate out of that plane, which means this really only has how many rotational modes? Yeah, just 1. This molecule, since it's trapped in this 2-dimensional plane, can only rotate within the plane itself. So it only has 1 kinetic energy rotational mode. There's no interaction with the other molecules because in a gas, we're assuming they're too far apart. And it also says the vibrational modes are frozen out. So we don't need to worry about the vibrational modes. Just the 2 translational modes, 1 rotational mode. So it looks like we've got a total of 3 modes per molecule. So that's what we would use in this 3 modes per molecule is what we're going to use in the Molar specific heat formula. So we fill that in. 3 times R over 2, or in other words, 1.5 R. So that's what I would expect for the molar specific heat. If you then wanted to find the heat capacity, which isn't what this problem is asking for, but if you did want to find the heat capacity, you'd multiply the molar specific heat, which is the heat capacity of 1 mole, times the number of moles, which would be 2 moles. So 1.5 R times 2 moles would be 3 R, and that would be the heat capacity of the entire sample. But this one's just asking for the molar specific heat, which means we're focusing on just 1 standardized mole. Any other questions on that so far?
So the answer is 1.5 R.
Yeah, that should be the molar specific heat, which means the heat capacity of exactly 1 mole.
Okay.
3R would be the heat capacity of the whole sample, all 2 moles of it, but that's not what this is asking. This is asking for the molar specific heat, which means the heat capacity, not of the whole sample, but the heat capacity standardized to 1 mole of the substance. So you could use this heat capacity formula, you'd just be using 1 for N because we're standardizing it to 1 mole. Molar specific heat literally means the heat capacity per mole.
So the 2 moles there at the beginning is kind of there to throw you off a little.
Yeah, I think so. I mean, it's the question is in part checking, do you understand the difference between heat capacity of the whole sample versus molar specific heat of the substance it's made from?
Okay.
And molar specific heat means we don't care how much of the substance there is, we're standardizing the value to assuming exactly 1 mole. Any other questions on that one?
So if the vibrational modes weren't frozen, would it still have 3 modes? Or would it?
If the vibrational modes were active, then we would have to include those vibrational mode, the internal vibration as well. Because within the molecule, the atoms could be vibrating against each other along the bond. And for that, I think you could just use the usual approach. How many modes would you usually expect for internal vibration for a diatomic molecule?
2, 1 for Ke and 1 for Pe.
Sorry, 1 for each what?
1 for Ke and 1 for Pe, or
Yeah.
is it 2 of each?
No, it should be just 1 of each because the bond can effectively be treated as one-dimensional. For a diatomic molecule, the internal vibration is just the atoms vibrating against each other as if the bond were a tiny invisible spring. So along that one single spring, along that one-dimensional bond, you've got 1 kinetic energy mode and 1 potential energy mode. If you sandwich them between these 2 plates, the bond is still one-dimensional. So you still have the 1 kinetic energy and 1 potential energy mode. So this molecule, if the vibrational modes were active, I would still assume 2 internal vibrational modes. So in this case, that combined with the 3 modes we already counted would be 5 modes per molecule total, if all the modes were active.
Oh, okay, got it. Thank you.
Mm-hmm. Any other questions on that one? And were there any other quiz questions you wanted to work on? Question 3, let me pull that up. There it is. Is this the one? Okay. So we want to find which statements are correct from all these statements. That's always a tricky way to phrase a question. Well, let's look at what we know first and then see if we can figure out whether each of these statements makes sense one at a time. 2 moles of a solid, 3 moles of a diatomic gas. Gas is initially at a higher temperature, but they eventually reach thermal equilibrium. So let's just make a list of what we know so far. We've got solid, which is 2 moles, and a diatomic gas, which is 3 moles. And initially, the gas is high temperature, the solid is low temperature, and then final is they reach thermal equilibrium. So they're both at the same temperature. In other words, the gas has lost energy, the solid has gained energy. And while we're at it, let's just list out a few other things we know. For one thing, I'm guessing that this is probably going to involve modes, just from the fact that we're talking about the gas being diatomic, and it looks like modes are mentioned in some of these statements. So for the solid, how many modes would you expect per molecule or per particle? Yeah, we should expect 6 modes. Because each atom in this solid can move in 3 dimensions and can also interact with its neighbors in 3 dimensions. It can be moving left and right, forward and backward, up and down, and it can be interacting with neighbors to its left and right, in front and behind, and above and below. So that means 3 dimensions worth of interaction and 3 dimensions worth of motion. So 3 kinetic energy modes and 3 potential energy modes, 6 modes total per particle. And if we wanted to find the total number of modes, we multiply the number of particles times 6 modes. And keep in mind that 2 moles means 2 times Avogadro's number particles. So to find the total number of modes in the entire solid, we multiply 6 times 2 times Avogadro's number, if we wanted to know the total number of modes. What about for the diatomic gas? Could be 7 modes per particle per molecule. Under what circumstances would we expect 7?
A high temperature.
Right. At a high temperature, we'd expect all 7 modes to be active. What if it's at a lower temperature?
Only 5.
Right. We could have 5 at, and I'm going to say a more moderate temperature. What if it's at a very low temperature? If it's very cold? What are the only modes you would expect to be active at extremely cold temperatures?
I don't know if we've really talked about that.
Maybe they kind of skipped over it. What I've usually heard is that the rotational modes can also freeze out if you get very cold. At around room temperature, you'd expect the translational and rotational modes to be active. At very high temperatures, the internal vibrational modes also activate. But at very, very low temperatures, I would also expect the rotational modes to be frozen out, which means you'd have the translational modes only. And how many translational modes would you expect? How many dimensions can it move in? Yeah, it should be 3. So at extremely cold temperatures, the particles can move, but they can't rotate because there's not enough energy for them to rotate. So you'd have only the 3 translational modes. Once it gets up to a more moderate temperature, like around room temperature or something, the molecules are also able to rotate. So you got the 3 translational modes and 2 rotational modes for 5 total. And then if it gets very hot, there's enough energy per particle that the atoms can vibrate inside the molecule. And so you've also got the 2 rotational modes or two vibrational modes for 7 modes total per particle. So the number of modes per particle in this diatomic gas is going to vary depending on the temperature. And if you take a look at any one molecule, it's either 3 or 5 or 7. The in-between values don't happen. But if you look at the gas as a whole, it's possible that maybe you're at some in-between temperature. Maybe some of the particles have 5 modes, some of the particles have 7 modes. So the average could be somewhere in between. Any one molecule has to have 3 or 5 or 7 in this case. But if there's a mix, then the average could be somewhere in between, including even non-whole numbers. You could have like the average number of modes per particle be 5.73 or something like that. But now that we have something about the number of modes, let me also list out, just for consistency, 3 moles means 3 times Avogadro's number of particles. So let's just take a look at these statements one at a time and see if we can judge each one of them for truth or not. First of all, if the vibrational modes of the gas are frozen, and right away that tells us how many modes. Yeah, we'd have 5 modes per particle. And then the solid has a larger heat capacity than the gas. And we already know the solid has 6 modes per particle. So if we know the number of modes, how would we figure out the heat capacity? Yeah, CV per mole. So we've got as we saw before, number of modes times R over 2. That's the heat capacity of 1 mole. But if we want the heat capacity, so CV mole equals this. But the actual heat capacity is all that times number of moles. So the heat capacity of the whole substance, I guess I should say CV because we are assuming constant volume here. So CV per mole is number of moles times R over 2. CV, the heat capacity of the whole thing, is N times all that. Because number of moles times R over 2 is the heat capacity for exactly 1 mole, also known as the molar specific heat. But the heat capacity of the entire sample is that specific heat times number of moles. Which means in order to compare these, if we want to know which one has a larger heat capacity, we should compare number of moles times number of modes times R over 2. But again, let's look at this in terms of what's actually different. What in this equation is not changing if we compare gas versus solid? Right, the R over 2 is just a constant. So we could just bundle those together and say heat capacity at constant volume is N times number of modes times a constant. And if we're just comparing values, if we don't really need to know what is the heat capacity, if we just want to know which one is larger, we can ignore that constant because it's the same for both. We can look at just what's left, N times number of modes. So if we compare those, for instance, for the gas, we've got 2 moles times 5 modes times a constant. Specifically, that constant is R over 2 if you need it. But for the solid, we've got, oh, sorry, the gas was 3 moles, wasn't it? For the solid, we've got 2 moles times 6 modes times R over 2. And again, the R over 2 we don't really need to worry about because it's the same for both. But if you compare 3 times 5 versus 2 times 6, what's larger? Three times 5, 2 times 6.
Times 5.
Yeah, 3 times 5. So 16 versus 12. So for the gas, the heat capacity of the entire sample is going to be 15 times R over 2. For the solid, it's going to be only 12 times R over 2. So the gas does have a larger heat capacity here. So this one is false. What about the next one? To reach thermal equilibrium, the gas must lose more energy if the vibrational modes are frozen than if they're active. As it goes towards the thermal equilibrium, it's going to be losing some energy. Any thoughts on that one? How could we figure out how much energy the gas is losing as a result of modes being active or not? Well, let's take a look at this in terms of conservation of energy. We know that we've got change in thermal energy of the gas plus change in the thermal of the solid. This is a closed system, so those should add up to 0. And you can always write delta E thermal as heat capacity times delta temperature. And I guess this whole thing is delta energy for the gas. We could isolate that just by subtracting the delta E thermal for the solid to the other side. But it looks like that just tells us that the change in energy for the gas is the opposite of the change in energy for the solid. If we change around the number of modes of the gas, does that influence anything on the other side of the equation? Probably does. I mean, C solid, that's just going to be the 2 moles times 6 moles times R over 2 we found earlier. But the change in temperature, I think, is going to depend on properties of the gas. Because the heat capacity of the gas, more modes basically just means it's more difficult to change the temperature. Because to change the temperature, you've got to change the energy per mode by a fixed amount. If there's more modes, that means you've got to change the energy more in order to get the same temperature change. So more modes means it's more difficult to change the temperature. If the vibrational modes are frozen, does that mean it's easier or more difficult to change the temperature? Vibrational modes frozen out. Does that mean more modes or less modes?
Less.
Right. Vibrational modes being frozen out means there's less modes available. And since changing temperature by a certain amount means changing the energy of all the modes, if there's less modes available, that means you have to use less energy transfer in order to change the temperature. So I would expect a smaller energy transfer if the vibrational modes are frozen. If they're active, there's more modes, which means it's more difficult to change the temperature. So I think that one would be false. And then if the vibrational modes are frozen, the solid has a larger specific heat than the gas. This looks like it's similar to the first one, except we're now talking about specific heat. I presume that means molar specific heat. So that means instead of using N times number of modes times R over 2, we're looking at just number of modes times R over 2. So if we take CVM, the molar specific heat capacity, we'll use number of modes times R over 2. And again, since R over 2 is a constant, we really just need to compare number of modes. It says the vibrational modes of the gas are frozen, so that's 5 modes. The solid, 6 modes. So can we say that the solid has a larger specific heat?
Yes.
Yeah, I think so. Because the idea here is the specific heat per mole depends only on the number of modes. More modes per particle, and this is not for the whole thing, this is just per particle. More modes per particle directly means higher specific heat. So if with the gas having the vibrational modes frozen out, it only has 5 modes. The solid has 6 modes per particle, which is more. More modes per particle directly means higher heat capacity, or sorry, higher specific heat. When thermal equilibrium is reached, average translational speed. The whole idea of average translational speed should only depend on the temperature. Because as we saw earlier, the kinetic energy of one molecule should equal 3/2 times kb times temperature. So it depends only on the temperature. We could replace this with half the mass times speed squared, as usual for kinetic energy. So if they're all at the same temperature, does that mean they're all at the same speed? Does same temperature have to mean same speed? What else could be different there? Because it looks like most of these quantities are constants. What's the one thing here other than the speed and temperature that is not the same for both molecules? Well, why would the velocity be different? We know the temperatures are the same. How is it possible that the velocities could be different? What else in this whole equation could be different from one molecule to another? Yeah, they could have different masses. Same temperature means same kinetic energy per molecule, but that only translates to same speed per molecule if the molecules are all the same mass. If they're different masses, then the more massive one will be moving slower, the less massive one will be moving faster. So same temperature just means same kinetic energy per molecule. That doesn't mean same speed per molecule because the molecules could have different masses. You can only assume that they're the same speed if they're the same mass also. So no, they are not going to be the same speed here. And lastly, the temperature of the system at thermal equilibrium is higher if the vibrational modes are active versus if they're frozen. I think that's going to go back to the idea we were looking at in terms of heat capacity as how difficult it is to change the temperature. Higher heat or more modes if the vibrational modes are active. More modes means more difficult to change the temperature, which means the gas is going to be cooling off more slowly. Fewer modes would mean it cools off very easily and quickly. More modes means it takes more effort to cool it off. And since the gas is cooling off, if the gas cools off more difficultly, the solid is going to rise up to meet it higher up. Whereas if the gas cools off easily, they're going to meet somewhere lower down. So yeah, I would expect more more modes active means higher heat capacity, which means it's more difficult to change the temperature. So the gas is going to have a more difficult time cooling off, and it won't cool off as much. Any other questions on that one?
Thank you.
You're welcome. See you next time.
Bye.